Okay, happy Wednesday, everybody. How's our first week going? Are we surviving? I see something like this. We're getting back into the groove. Okay, so today, technically, which is a loose term, the first Learn Smart was due. But online it says it's not due till Friday. Again, that's just to make sure everybody's getting Connect to work and we're all on board with how that goes. Okay? So technically all of these Learn Smarts that are from Chapter 13 are due Friday at 11. Okay, so all of our Learn Smarts and our quiz homework type things on Connect are going to be due at 11 a.m. that day of class. Okay? It looks like when I just checked before class that about 130 of us are signed up for Connect. So 130 out of 145 is not so bad. Okay, if you are in that 15 that have not signed up for Connect, if you're having a problem with that, please let me know. All right, because starting Friday, those grades will start to count. Okay, so I don't want you to miss out on those points. There's also that survey on Canvas, which also about half of you have already done. Again, I hope everybody got my announcement that even though I told it there's no right answers, it tried to mark you wrong. Okay, they're how you feel about the course, so obviously none of them are wrong. All right, that's due on Friday. The link is in the on our syllabus. We have no class on Monday. All right, but you do have a homework quiz due on Wednesday. All right, so if you're looking to have a sweet long weekend, try to get that done sooner than later so you can enjoy the day off. Okay, so today we're going to talk more about how intermolecular forces, temperature, and pressure affect solubility. But I did promise you a syllabus quiz, so that's what's going to happen to start. All right, our clicker, you won't see that any of our clickers from Monday worked. Apparently I was logged in as someone else, so I have no access. Somebody else has access to our clicker file from Monday. Okay, but it says that it's me, so we're hoping it works. We have channel 41, and also if you have the app on your phone, the session ID. So I will try to post those Canvas or those clicker scores on Canvas right after class to make sure everybody's clicker is up and running. Okay, so our first question is, how many in-class tests count in your semester grade? Not counting the final exam. Okay, so we're not talking about the final exam. How many tests are we going to have, and how many count for our final grade? All right, let's see if we can make it over 100. Oh, okay, ready? Last responses. Stop. 4. Perfect. Okay, there are going to be 4 in-class tests. They all count. Okay. All right, our next one. Why can I not? Here we go. What does LS stand for? When you see that both on the syllabus and on Canvas, what does LS stand for? Learn something? Yeah?
So it's like 1A.
1 can be, yep, either you can 1A, 2B, 3C. I believe if you enter the number, it also will work out. All right, let's see. Learn Smart, perfect. Okay. I like Let's Start also, throwing 1 in there. All right, let's see what we got next. The final exam covers just the last chapter, just Chem 132, or both material from Chem 131 and 132. All right, we were listening on Monday. High five, right? This is the whole year's worth. 131 and 132 will be on the final exam. Okay, so now we're going to see if we can get a little chemistry in there. Ooh, I lied. Okay, where can I find the answers to the end of the chapter book exercises? All right. Canvas, perfect, okay? All of the solutions to the end of book problems are on Canvas. All right, please use that to your advantage while doing those homework problems in the book before you do those quizzes on Connect. That will be really helpful. All right, now I think I'm not lying about chemistry. Okay, which can participate in hydrogen bonding? Okay, I have ethanol, methylamine, HF, all of those or none of those? All right, let's count it 3, 2, 1, stop. Okay, so let me see. We got most going with D, which is all of them. That is what we're looking for. Okay, so I have to have that hydrogen bound to an oxygen, nitrogen, or fluorine, and this would involve hydrogen bonding within that particular material. Okay. All right, and lastly, which of the following have dispersion forces or dispersion intermolecular attractions?
If it's A, B, C, D, which is
So if it's A, B, you mean if you're trying to go with this guy?
yeah.
Okay, I think if I say, yeah, hold on, let me stop it first. Let me give you 5 responses. Sorry. Okay, let's give that another whirl. Everyone's like, we know now. All right, so we're looking for all of them, right? No matter whether you are polar, non-polar, everyone has dispersive forces. That's excellent. Okay, so let's get started today. I just wanted to, because I had a feeling that everybody could not see what was on the board as we ended class on Monday, and I finally got the pen to work, that I just wanted to make sure we felt okay with this solution process. And so I wanted to show you guys that here in the hydration, right, we also have Cl minus gas going to Cl minus aqueous. Right? So in that overall process, which is the most important, I'm going to take the delta H of lattice and the delta H of hydration and put them together to form my delta H of solution. All right, so I'm going to write my NaCl solid goes to Na plus gas plus Cl minus gas. All right, and this is delta H of the lattice. I did start recording, yes, but thanks for reminding me. So that's my delta H of lattice. Okay, my other part is that delta H of hydration, which is now to take my gaseous ions, okay, and get them into the aqueous form. Okay, and this is the delta H of hydration. Okay, so if I want to combine those two, do you remember that law that we're going to use? Hess's law. Yeah, perfect. Okay, so I can cross out my gaseous species because they're on opposite sides, and I'm just then going to carry down what I have left over. So I have sodium chloride solid goes to sodium chloride or sodium cation aqueous plus Cl anion aqueous. Okay, and overall, sorry because I'm going to run out of room on this corner, this is the delta H of solution. Okay, so again, the overall process, delta H of solution is equal to the delta H of the lattice plus the delta H of hydration. Okay. So I wanted to make sure that we just had that visually because I felt as we sort of scrambled at the end of class last time that could have been a little bit confusing. All right. Okay, so we're really focus today on how these different forces, intermolecular forces, as well as temperature and pressure, play a role in the physical properties of a solution. So if I'm thinking here about my intermolecular forces, I know that increased strength, okay, of these interactions all right, and you guys, if there's something that you can't read while I'm writing it up here, please let me know. Okay, I like to think I have okay handwriting, but writing with this pen is not the easiest thing in the world to do. So just stop me if you can't see anything. Okay, so these increased strength of interactions means you have an increase in the energy it takes to break them up. Okay. So I have to put more energy in, or if I'm thinking about boiling point, which we're going to do here in a second, I have to have a higher boiling point if I'm disrupting those strong intermolecular forces. The other thing I wanted to touch on a little bit here was something that's in one of those review PowerPoints that are posted on Canvas, is the word polarizability. Okay. Okay. So polarizability is just what it sounds like. The ability to form a pole in a nonpolar compound or molecule. Okay, and the fancier way of saying that is your ability to distribute charge. Okay, charge, or I'm going to say electrons, depending on which nomenclature you prefer. Okay. So do we think that it's easier to form a pole or distribute electrons in something that's small or something that's large? Okay, again, let's think about it. If I'm trying to distribute, let's just think about a ping pong ball bouncing around in something, right? Does it have more space, a ping pong ball inside of, let's say, a softball, or inside of a large beach ball? Beach ball, right? And I like to do what in 131, which my students call the fluffy atom dance. Okay? So when you get a lot of electrons, okay, the larger your mass, the more electrons you get, you start to have this like fluffy cloud of electrons around you, okay? And the fluffier you are, the easier it is for those electrons to move within that space. And if that's true, you can form a stronger dipole in that material or that compound because the electrons, right, as let's say you have an electron approaching, as you approach, there's more space to run away. Right? If you're something really small, you don't have the ability to distribute your charge within. Okay, so if I'm talking about in these dispersion or polarizability in nonpolar molecules, I'm really focused on what that does to molecules that only have dispersion forces, or if I have to break a tie with someone that has very strong, let's say, hydrogen bonding or other intermolecular forces that are up there on the strong scale. Okay, so let's think about this first one here, where I have ACH3, CH3 versus ethanol here, okay? And I want you to chat with your neighbor, okay? You both can enter the answer here, but chat with your neighbor about which one you think has the higher boiling point and why. And if you don't know your neighbor, say hello and tell them your name. All right, let's try to get our final answers in here. I'll give you a 5, 4, 3, 2, 1, 0. Okay, we made it over. All right, I like choice B. All right? Okay, so what kind of intermolecular forces does... Now you're not going to write again? Okay. There we go. What kind of intermolecular forces does choice A have? London dispersion, dispersive, right? It's nonpolar, only carbons and hydrogens. All right, how about choice B? All right, so there's this handy little thing hanging out here at the end, right? That is a hydrogen bound to the oxygen, so it can have hydrogen bonding. It also has dispersion, right? So I have dispersion and H bonds. But that hydrogen bond, right, is the second strongest intermolecular force you can have, as we saw on Monday, that list of intermolecular forces. Okay, so that baby wins. This has a higher boiling point. All right, now what if we look at the next one? Again, this is the same, right? So he has dispersion. What does propane have as its intermolecular force? I can hear you. You can't all count on Yusuf answering your questions for you, okay? Creepy, isn't it? I'm good with names. All right, so is B polar or nonpolar?
Non-polar.
Nonpolar, right? If I'm nonpolar, my only choice is dispersion. Okay, so now I'm in a dispersion versus dispersion category. All right, so I have to rely on that polarizability, okay, or my ability to distribute charge in that molecule. Sorry, I keep saying material because I just taught polymer chemistry in the fall. It's a word I had to use over and over again. Okay, so this baby, again, is going to have the higher boiling point. Okay, now if I look at the third example, right, they both have hydrogen bonding. Okay, they both have dispersion and they both have H bonds. Okay, but again, if I'm relying on H bonds and dispersion, right, dispersion here of the larger carbon-hydrogen chain is going to win out. Okay. And how about on the last one here? Okay, let's again chat with our neighbor about what we think is going to have the higher boiling point. Okay? A or B?
I don't know. That's like induced. B is induced. I don't know what ion it is. So dipolar is polar and non-polar. Ion is dipolar and ion is what I have. I'm still going to be like, you ask me why I would say
All right, let's see how we did. Let's see if I can get to 100. Okay, nailed it. All right, so we have a pretty overwhelming choice of B. All right, and it could be because the pattern. Maybe we're just saying they're all B's, but B is the right answer. Okay. Oh, my bad. Okay. Okay, so B, really? Just when you think it's working for you today. Okay, let's try it. Okay, so B is the right answer. And you probably were debating, right, because they both have hydrogen bonding, they both have the sort of same number of carbons, right? They have this 2-carbon chain on the inside. But I'm going to say people probably went with B if it was not a guess because it had more than one hydrogen bond. Okay, so if I have 2 hydrogen bonding capabilities, that's going to double my ability to form actually a network throughout the molecule, because we're again talking about the interactions just with these molecules with themselves, not any other things in solution. Okay, this is not a solution, this would be a pure solvent. Okay, so actually A is ethanol. Okay, ethanol has a boiling point of 78 degrees. All right, this molecule over here is ethylene glycol. Has anybody heard that word before? Jeremy's shaking his head. Okay, I'm from upstate New York originally. All right, when I left my parents' house to come back here, it was like -8 outside. Not feels like was like -15. Okay, and I'm driving down the road and there's salt all over my car and my windshield washer fluid does not work. That's not good. Okay, you saw people all over the side of the road pulling over and throwing snow onto their windshield because everybody was having this problem of frozen windshield washer fluid. Okay, I made the ingenious idea, don't try this at home, to take the gallon of windshield washer fluid while I'm driving on 81 at 80 miles an hour and fling it, open the window and go like this in hopes that it's going to run down my windshield. Because God forbid I pull off the side of the road and take 2 minutes to get a clean windshield. Well, that doesn't work. Don't try it, right? It just blew all of it all down my arm. So now I have my arm outside. It's covered in windshield washer fluid, ready for an 8-hour trip back to Virginia, okay? But the difference is that windshield washer fluid you buy in Virginia is not rated for that temperature. Okay, the windshield washer fluid you buy in New York State has a melting point down to -20. Okay, so ethylene glycol is antifreeze. All right, it's also potentially one of the compounds they now put in, vape that people vape with, which is why it makes that really terrible smoke. And if they have ethylene glycol, they're really bad for you. Okay, just throwing that out there. Just a lot of useful tips today. Lecture. Okay, but ethylene glycol has a boiling point of 197 degrees C. Okay, so that's a really impressive increase in boiling point just from putting that extra link on there, that extra hydrogen bond. Yeah.
I was wondering, so if you have like an oxygen nitrogen formula, but in the structure, if they're not bound to each other, is it still hydrogen?
Okay, so the question is, and I was listening to some old recordings and you can't necessarily hear the question, so I'm just going to repeat your question. If there is an oxygen and hydrogen, or let's say nitrogen, fluorine, and hydrogens in the structure, but they are not connected, can you have hydrogen bonding? No, you cannot. Okay, so you have to have, and that's why they're written like this, to show you that hydrogen is connected to the oxygen. Okay, if you have some other wild and crazy organic structures, I'm going to say that's a slight lie. Okay, and the longer you take chemistry, the more you know that that's a little bit of a lie, but for us right now, you have to have that hydrogen bound to one of those atoms.
So in the formula, you won't have the hydrogen and that atom next to each other, it will be like next to each other.
Correct. It would have an oxygen. So let's say it was like CH3O CH3. Okay, that baby cannot hydrogen bond for us. Okay. Okay. Okay, so now I want to talk about, just a little bit more about these boiling trends. I'm going to move this down so we can see this figure. This is figure 12.15. All right, and as you can see, what we got going on here is that we have boiling point on the y-axis, and we have the period on the x-axis. Now, I think I may post for you guys a printable periodic table if you don't already have one, because in the redo of this room, there's no periodic table in this classroom, which can be kind of a bummer. All All right, but what we're looking at as we increase the period, right, we're going down and we're getting more electrons, we're getting an increase in molar mass, and we have an increase in the boiling point. Okay, so that's also what I have sort of depicted down here in the low boiling point up to high boiling point. All right, so for a general trend, we're going to have an increase. Okay, so an increase in molecular weight, okay, results in an increase in boiling point. And this is because of that polarizability, or because of an increase in polarizability. All right, and sorry, this again is nothing. All right, and that increase in polarizability again happens because we have more electrons, and therefore we increase our dispersion forces. So as we go down a period, right, I go from sulfur to selenium to tellurium, okay? Those atoms get larger, they get more electrons, and I can see that I have this increase in boiling point as I go from sulfur up to tellurium. All right, and the same is true for these other compounds. However, I'm missing something here, right? Above sulfur on the periodic table is oxygen. So I'm missing water in this particular graph. I'm also missing methane. All right, so what happens if I thought about the trend following, water should have a boiling point down here. All right, if that trend were to follow. Okay. But we know that water has those special type of bonds that we've been talking about. Right, so in the special case where you have hydrogen bonds, okay, that's going to drastically increase the boiling point. Okay, so in this table on the bottom, I'm really going to have water above this. Okay, in my next one, okay, I also get NH3 above. Okay, NH3 can hydrogen bond, as well as HF. Okay, but then you have lonely methane down here. Okay, methane follows that trend because just like its other components, it only has dispersive forces. Okay. And it is significantly smaller, has less electrons than the silicon hydride, or silicon, germanium, or tin species. Okay, so it really goes to show you that you have the serious power of hydrogen bonding and what it's capable of doing to the physical properties of our materials. Okay, so those are talking about intermolecular forces and what they do to the physical properties of pure molecules. All right, so these are they're only interacting with one another. This is not a mixture of different components. Okay, but what happens when you go and you try to mix stuff? Okay, so let's look at our first one here. Okay, again, you can talk with your neighbor. So if I have sodium chloride, is it going to dissolve better, I'll say, in methanol, or the C6H6 is benzene? All right, talk with each other about what type of intermolecular forces are happening between these components. Yeah, you're like, don't overthink yourself, right? All right, let's try to make it to 100 here. Okay, so let's see what we thought. Okay, so we're torn. Okay, we're torn. Now, before we answer again, all right, let's think about this a little bit. Sodium chloride is ionic, right? Why every time we change does it not? Let's see. Okay, so sodium chloride is ionic. That is an ion-ion interaction. That is the strongest type of intermolecular force, right? That's so strong that it becomes an actual bond, right? You have an ionic bond between those two. Okay. What type of intermolecular forces does methanol have? Okay, so I'm hearing both of those. Dispersion and H bonds. Okay. How about benzene? C6H6. Dispersion, right? He is not polar. I have only carbons and hydrogens. Okay. So again, I'm going to ask the question again. We're looking to match the best intermolecular forces. Right? That old adage, like dissolves like, right? I want to have the best or the closest pair on that list of intermolecular forces. All right, so let's give this another whirl and see how we do. All right. All right. All right, I like A. Okay. Well done. Okay, when we think about it. So if I think about another example here, or not. Okay, if I'm thinking about C6H14, okay, that baby only has dispersion. Right? He's nonpolar. I only have carbons and hydrogens working. Okay. Again, in my methanol, I have dispersion and H bonds. But now maybe I'm stumped again. This also only has dispersion and H bonds. Okay. All right. So I want to think about, right, this is pretty big, 6 carbons, right? Pretty fluffy, can do the fluffy atom dance, okay? And that's going to be, okay, Omaha, Nebraska is calling, silence them, okay? So you guys get a lot of random calls. I'm supposed to bring my phone in case we have an emergency, but it's buzzing over here out of control. But you're right, I'm looking about this polarizability difference, and that's going to make this the right choice. Right? Because again, I'm looking to think about like dissolves like. All right, and you want to be careful about how you think about that list of intermolecular forces, okay? Because you might be inclined to say, all right, I'm just going to pick that it dissolves in whichever one has the strongest intermolecular force. Okay, like regardless of what it is, if H bonding is there, I'm going with that. Okay? But that's not the way you want to think. You want to think that like dissolves like, meaning the closest partner match in intermolecular strength is going to be the best solubilizing component. Okay? So you want to be careful, again, of looking back on Monday's lecture notes to see that ranking of intermolecular forces. Okay. And then viewing how we think about polarizability. So if I am in a tie, right, that increase in polarizability is going to let you win out in one system over the other. Yeah?
Is dissolving and mixing like synonymous, or are they the same thing?
Okay, is dissolving and mixing the same thing? So if I mix sand and water, does the sand dissolve? No. Right, or else the beach would not happen, right? So, but salt, if I mix salt into water, it dissolves. So you have to be a little bit careful because the word mix is a little, it's a verb, right? So I'm mixing, but if I'm asking you, do these two things mix? I would rarely probably say that on a homework problem. I would say, does this dissolve in this, or which one more readily dissolves, Okay, but that is a really good question because you can mix anything, right? You really can mix anything, but it doesn't always dissolve. And that is a good question to say, okay, I have sodium chloride and I have sand, and I'm going to mix them both into water. Which one dissolves? Okay, so, but that's a really good point to be reading the nomenclature or reading that question very carefully to know what it's asking you for. Okay, let's see. Okay, so then I just want to do a couple of quick definitions here. Okay, so a solution, by definition, is equal to a solute plus a solvent. Okay? And that solvent is going to be in the majority phase. All right, or you got lots of it compared to the solute. And for us, for the majority of this semester, that's going to be water. Okay, and that's why we talk a lot about the intermolecular forces with respect to water and these other components, because it's very often used as the solvent. Okay, and our solute is what we're trying to dissolve. Okay. All right, then we have a saturated solution. Okay, and the saturated solution is the max solute that will dissolve. Or I should say max solute that is dissolved in a solvent. Okay. If I add any more solute to a saturated solution, it will precipitate. Okay, so any more will precip. Okay, so is there a standard unit of volume that you measure it by? That's actually where solubility comes into play. Okay, because solubility is the specific amount of solute in a certain amount of solvent. Okay, so I think sodium chloride is like 35 grams per milliliter. Okay, if I do that solubility at a particular temperature, it will be a saturated solution. Yeah?
For saturated solutions, is there like this, like, given like temperature set that it would be?
Absolutely.
Or should it not be super saturated?
Absolutely. So the question is there a specific temperature? And temperature 100% plays a role. So for any salt or anything that has this finite solubility in a solvent, that is at a particular temperature. Okay. So I also heard the word supersaturated. Okay. So supersaturated means I have more solute than I should in the solvent at that particular temperature. Okay. That's how the good old sweet tea is made. Okay? Again, I am from upstate New York. I think sweet tea is disgusting. I apologize to everyone who loves it. Okay? My husband thinks I'm a complete weirdo, but I can't stand it. All right? But to make tea that sweet, it is above the saturation level. So, right, when you make sweet tea, you do the extraction of the tea, and it's warm when you add the sugar. Okay? And then you cool it slowly so that all of that sugar stays in solution. Okay? You may notice some people have a little bit of sugar laying on the bottom of their pitcher of sweet tea. Okay? Because as it cools, all right, and if you hit it in the refrigerator, okay, some of it may precipitate out because it is a saturated solution. Okay? You can also have an unsaturated solution. All right, and that would be at a given temperature that you have less solute than will dissolve. Okay? So there's a lot of ways. Also Kool-Aid. Again, Kool-Aid you should heat up because it always has some sludge when you get down to the bottom. Okay? It's above its max solubility of sugar in there. Nobody drinks warm Kool-Aid. No, I'm with you. But I'm saying, like, when you get down to the bottom of the Kool-Aid, it has a different viscosity. It's a little thicker there on the bottom than it was on the top. Okay, and you can almost, re-dilute it Get a little more water, get a little more, bang for your buck on the Kool-Aid. Okay? I also had a friend in college that told me you didn't have to add sugar to Kool-Aid. You just buy the packet. I was like, no, you have to add sugar. He's like, the packet smells delicious. It's going to be great. I said, okay, you drink it. Tastes like crap, right? You need like 2 cups of sugar to make Kool-Aid taste good, because red food dye by itself does not taste delicious, okay? But red food dye plus sugar, great, okay? Okay, so we're going to talk here a lot more about solubility, okay? And again, how that depends on intermolecular forces, which we're all professionals at, but also how temperature and pressure affect solubility. Okay, so I know that intermolecular forces are going to come into play here, and again, I want to be thinking about like dissolves like. Okay, but when I think about, again, I said for the most part, our solvent is going to be water. We're going to talk a lot about aqueous solutions, and a solute is more likely to dissolve in water, okay, if it has a few of the following properties. One, okay, if it also has H bonds, right? Water is great at hydrogen bonding. If my solute also has hydrogen bonds, awesome. That's going to be a great like dissolves like. Okay. Also, okay, stronger dispersion. Okay, because water has a dipole. Okay, if I'm something that's nonpolar, my ability to have an induced dipole will help with that solubility in water. Okay, number 3 is a weaker salt lattice. Okay, and that comes from the lattice energy, right? How we started class today. I have to break that salt apart. So the weaker that interaction, the more readily it will dissolve in water. All right, and 4, okay, I'm looking for no or a short greasy, okay, which is lots of carbons bonded to hydrogens. They make things greasy, okay. Short, greasy, nonpolar ends. All right, I'm going to try to show you a couple examples of that here. Okay, so I like to think about sodium chloride versus magnesium chloride, or also versus magnesium sulfide. Okay, so if I'm thinking about sodium chloride, sodium is a +1, chloride is a -1. Okay, how about magnesium? Do we know what the charge on magnesium is there? +2, look at that. Okay, +2, Cl is still a -1, and if I'm thinking down here, this is a -2, my sulfur. Okay, now, if I'm looking at sodium chloride versus magnesium chloride, okay, magnesium chloride is going to be more soluble. And that actually comes from an increase in the delta H of hydration, because magnesium is a +2, so now 2 waters can run up to it. Okay, so the waters really want to surround that. Okay. But what about the difference in lattice energy? Okay, let's now think about lattice energy between sodium chloride and magnesium sulfide. Okay, I want you to chat real quick with your neighbor about that. Okay, and see, we'll go, this guy would be 1 or A, sodium chloride, and a magnesium sulfide would be B. Which is going to be more soluble in water? Does the what?
It's like the state that it's in matters. Like
They're both solid. They're both solid. So I'm trying to put them both as solids into water. But technically, no, you mean like if you had a liquid versus a solid and you're trying to dissolve it? No, the liquid-liquid solubility is called miscibility. It's a different term, but that's whether they mix, completely dissolve into one another. Okay, let's see how we're thinking here. Okay, we're torn again. Okay, I like it when we're torn. Okay, because that means we're thinking about multiple things here and we're not sure, which is totally okay. Okay, so I'm going to refer back to thinking about lattice energy with respect to these two, sodium chloride versus magnesium sulfide. Okay, and you have to think back to good old Coulomb's law, okay, or Coulombic attractions, which means the bigger the charge, the bigger or weaker the attraction is. Okay, let's think about it again. The bigger the charge, bigger or weaker attractions? Bigger. Okay, so the bigger the charge, the stronger the attraction to the two are, and that means that magnesium sulfide is going to have larger lattice energy. Okay, if I have a larger lattice energy, that means I'm going to be more difficult to dissolve because I have to break them apart. So, whoa, okay, I don't need that. Weekly scan, why is, okay. Okay, so that means that sodium chloride is going to be more soluble in water than magnesium sulfide. Okay, and if I wanted to look back at good old 131 solubility rules, in fact, magnesium sulfide is not soluble in water. Okay, that's what a big deal lattice energy means to the solubility. Okay, really trying to break up those Coulombic charges takes a whole lot. Okay, so now if I'm again thinking about something like ethanol versus ethylene glycol, okay, again, this guy has more hydrogen bonds. It's going to be a better match for water. Okay, ethanol is still soluble in water. Okay, it doesn't mean that it's not soluble. We're looking for the more soluble compound. Okay, how about helium and xenon? Okay, are they polar or non-polar? Non-polar, so I'm only thinking about what type of forces? Dispersion, okay. Who's more fluffy? Xenon, okay. That means water can induce a larger pole in the xenon. Okay, and lastly, here I have methanol versus hexanol, and in this case, it's going to be methanol is more soluble because I have reduced, right, this has a really long greasy tail. Okay, so I've shortened that guy up. Okay, so where we are, because I think maybe I can get a couple more things in here. Let's see, we'll try not to get too behind on our first week. That's what happens, and Jeremy, I'll tell you, I can get off track telling you crazy stories about myself and traveling and all sorts of things. So I'm trying to stay as much on track in our first week as possible. Okay, so that's intermolecular forces. The other two are temperature and pressure. Okay, this graph here is the salt solubility. Okay, so salt is not just sodium chloride, right? Salt is a general term about ionic compounds. Okay, so I have this plot here where I have temperature right on the x-axis and solubility, and in this case solubility is given in grams of solute per 100 grams of water, and I have a number of different salts here. Okay, so as I increase the temperature, what does it look like is happening to the solubility? Is it going up or down? Up. Okay, so as I increase this temperature, let's take KCl for example, right? At 0 degrees, maybe only 28 grams are soluble, but at 100 degrees, I'm at almost 50 grams. Okay, so as I increase the temperature, I increase the solubility. Now, obviously, there are exceptions here. As you see, this cesium sulfate just sort of plateaus out, and we're not going to worry about any of those exceptions in the scope of this class. Okay, but I'll leave you with one more clicker question. Let's call this one number 1 and this one number 2, or A and B. And let's see if we can decide if this means that salt solubility is an endothermic or exothermic process. Okay, I want to think about that. I'll try to help as we're thinking about it. As I take salt solid into cations and anions, aqueous.
No, first solubility. So pretty much is what she just wrote.
Okay, so do I put, which side of the equation do I put heat on is where we're going?
You need energy to break the ions.
All right.
So I put endothermic.
Okay, endo. That's really well done, guys. Okay, so it is endothermic. Little jerk. And heat goes right in here. Okay, so we'll start there on Friday. Remember, those Learn Smarts are due on Friday. Okay, as well as that survey.